get major mergers indicated here in this plot trigger starbursts, that means short depletion times. And it seems to coincide with strong tidal compression. So we have this causal effect that we knew existed in isolated setup, in isolated galaxy. It's still true in cosmology and also through cosmic times. Not valid all the time. You see that the first one, for example, it doesn't have a big effect. It's really not doing what you expect. It's not valid all the time because you need to have this strong response of the galaxy. You need large-scale, coherent response of a disk of the galaxy. This means that you need organized motion. You want this packet of gas to respond in a similar way than this packet of gas. Otherwise, it's just complicated chaos almost. So this means that the disk has to be in place to do that. And that's why it's not active very early on. Alvaro will tell you much more about that this afternoon, and in a paper that he got accepted a few hours ago. And Oscar will link that to the formation of thin disk on his talk on Thursday. So now if we start from this link between starbursts and mergers, what we would like maybe to quantify is how the depletion time on the x-axis relates to the specific star formation rate on the y-axis. So basically how star formation rate normalized to the gas mass relates to star formation rate normalized to the stellar mass. If we look at this simulation, we can identify different phases. So the first, what I call the early phase, so between, say, redshift 10 to redshift 4, not much of a correlation between the two quantities. It's kind of a mess. It gets worse later in starburst phase. We have short depletion times, but really no clear correlations between the two. And it doesn't get any better after the last major merger in the secular phase of evolution. So that tells us that the depletion time and specific star formation rate do not correlate. It strongly varies between the phase of galaxy evolution, between the disk formation after the last major merger, and between in the starburst growing phase. Why is that? Well, if you think of that, it's not really surprising that the two quantities are not telling the same story, because the depletion time is a kind of instantaneous marker of your star formation activity, how fast you're burning your gas reservoir at the current star formation rate. While the specific star formation rate is normalized by the cumulative buildup of all the stellar mass you build up in the last billions of years. So it's much less correlated with the current activity. So that's an important point to understand why, if we convert these quantities into offset above the main sequence, you will still not get a correlation. That's what I'm showing here, again using a simulation, depletion time versus offset above the main sequence. And to define the main sequence, here I adopt the observational motivated definition from Linda Tacconi that depends on the stellar mass and the redshift. So I divide the SSFR from the simulation by this observational fit, and I get no correlation at all between the two quantities. So at this point you might say, yeah, okay, but that's because your simulation is not reproducing galaxy on the main sequence, and this definition is not appropriate for the simulation. Fine. There I show the normalization by the main sequence I would use, main sequence in quote I would use from the simulations, which is basically just smoothing out the star formation history, removing the peaks, and you see again that it's a mess. So we have the same story here when considering the offset above the main sequence, no correlation with the depletion time. So that means that starburst and offset above the main sequence are two different things. And this confirmed what has been observed recently by the group in Saclay, for example, that they detected starburst galaxy within the main sequence. So clearly there is not a correspondence between the two concepts. If you push the argument further, that tell you that the bimoty in SSFR, if you believe in these kind of things, but I will not enter the debate, it cannot be caused by starburst, at least not at all by starburst, because you don't have the correspondence between the two quantities. So why is that so important to understand how starbursts work in galaxy evolution? Because that gives you a time scale. Starburst means short time scale for star formation, and you can compare this time scale to anything else in your galaxy, including the time scale for chemical enrichment, for example, so in Fe. So if you do that during a starburst, you form stars so fast that you don't have time to reach the type 1a stage yet. So the type 2 supernovae, core collapse will increase the production of alpha elements, but not Fe yet. They have not kicked in yet, which means that you will boost temporarily the alpha over Fe ratio. And that's quite important because you can trace that in observation of stellar populations, for example, in the Milky Way. So that's the typical plot that people working on this would show, the meticity on the x-axis and the alpha over Fe ratio on the y-axis. Here I'm using a simulation again to plot every dot is one star-forming event. They are not all there for clarity, but some star formation events, and the color of the dots is the log depletion time. So what happened? If we start chronologically, very high redshift, we start at low meticity, you don't have starburst yet. Major mergers, no starburst. Alvaro will explain why. Later, you get this merger-induced starburst. So you boost your alpha. Fe is not reaching high values yet. So you have these little spikes in purple that you see here. Short depletion time, you go up in alpha over Fe. At some point, the type 1a supernova kicks in, and you go down. This is more or less what happened all the time when you don't have major mergers anymore, so after the last merger. And you can go to this low alpha over Fe sequence. So after the last merger, less tidal steering, less things going on, less large-scale injection of turbulence, which means less star formation, so low star formation rate, slower star formation, long depletion time, these things are not the same, and slower replenishment of your gas reservoir, especially if your galaxy has grown its mass. So that allows the transition to the next stage, the secular evolution, the adulthood of your life. So everything I told you so far is evolution in cosmological context, and I focus mainly on the effect of mergers. But at the same time, the galaxy is also evolving by itself, intrinsically. So how can we study this effect and compare to this cosmological? Ideally, we'll just remove the galaxy from cosmological simulation and run it in isolation. It's a bit complicated to do that from a technical point of view, but we can very easily do simulation of isolated galaxies. So that's what we did. We ran a suite of 18 simulations of isolated galaxies. I spare you the technical details are here if you want to know a bit more. And we run all the simulations keeping everything constant, all initial conditions being the same except the gas fraction. So we vary the ratio between the mass of gas and the total baryonic mass. The one you're looking at here is 10% gas fraction, so representative of local local universe galaxy. But we also did 25% and 40%. So again, only one variation of the gas fraction. So basically, you are seeing here gas-rich galaxy as they would be at redshift 1, 2, 3. But this is not the same galaxy evolving in time because I kept the mass and the size constant. Right? So there's a little bit caveat here. So using this simulation, we can have a look at what the morphology looks like in atomic phase, molecular phase, and stellar phase. At 10% gas fraction, you recognize the classical spiral structure. If you squint a bit, you see some star cluster in there, giant molecular clouds. Doing the same at high gas fraction, 25% and 40%, you don't see these spiral structures anymore, but instead massive clumps, some sort of elongated structures, but not really spirals. So that tells me that there is a clear dichotomy between the gas poor or low gas fraction and gas rich. At low gas fraction, I found spiral arms. At high gas fraction, I found giant clumps. This is not new. This has been seen observationally in simulations by many, many people. Many of you have worked on that. But we see that this transition seems to happen at gas fractions around 20%. And what we see in the morphology, we also see in the kinematics. This is just flashing the work from Florent Renaud during a master work in Lund. She measured the velocity dispersion, vertical velocity dispersion of the stars at birth as function of gas fraction. If you have a gas-rich galaxy, the velocity dispersion is relatively high because of the gas-rich clumpy structure. But at lower gas fraction, it quickly drops to more local universe values below gas fraction of 20%. So if I want to quantify that and to understand where it's coming from, I have to study the stability regime of the galaxy. First thing that would come to mind is to use the Truman Q, so the ratio between rotation and pressure to gravity. But this formalism has a big problem. Actually, it has 3 big problems. This means your disk is axisymmetric, rather thin, and only one component. So 100% stars or 100% gas. Clumpy disks are not axisymmetric, they are not rather thin, and they are not 100% component. So rather than using that, I'm using the much more adapt criterion, which is the Roman-Fallstadt parameter. So I will steal 2 Morris parameter, I will put that in this geometric mean, and I will sum up on 3 components, H1, H2, and stars. And following Roman-Fallstadt, I will have this weight factor. So W tells you how different you are from the most unstable component, and T accounts for the disk thickness, so correction factors. And using that, I can actually map instabilities in my 3 galaxies at 10%, 25%, 40%. We can study that. I think it's not the most important effects or the most interesting. What is much cooler is to look at what drives the instabilities. So here again are maps. If you are in yellow region, instabilities are driven by stars. In green, it's molecular gas, and in purple, it's atomic gas. Even more interesting is to plot that as a function of gas density. So here, the mass fraction in instability driven by stars, molecular and atomic, as a function of gas density, for 10%, 25%, and 40% gas fraction. So there is a lot of information in this plot. But if we focus here on gas-rich galaxies, intermediate density, so typically in between the clumps, what you see here is the gas takes the dominant role in the stability regime in between the clumps. And it's quite important because, by definition, what is in between the clump is what will be used to form clumps eventually. So this means that the gaseous phase sets the formation of the clumps. If you go to higher densities in the clumps themselves, then you see that the stars are taking, again, a dominant role, more or less here. And this seems counterintuitive that if you go to the densest gas phase, then the stars are playing a more important role. But it totally makes sense if you think in terms of feedback. In these star-forming clumps, feedback will inject turbulent support to your gas phase, and it won't, at least not directly, affect your stars because of their tiny cross-section. That means that the gas becomes very stable, and the stars become the dominant driver of instabilities. So talking about these clumps, we could look at their mass function and how it changes with the mass of gas. Or we already have an idea of that from the maps, from morphology. But here you can see the difference between 10, 25, and 40%. I put some slopes to get your high, and for the same price, I give you a Schechter fit, so power law with exponential cut. And what we see is that the clump mass function steepens with decreasing gas fraction, and that it's compatible with the Schechter cut at high gas fraction only. It doesn't really work for lower gas fraction. I'm still trying to process this. If you have some ideas or some input on that, I would be very happy to hear from you. But what we can say here is maybe there is a link with initial mass function of globular cluster or clusters in general, which is supposed to be a power law of -2, or maybe it's like I'm opening Pandora's box here, but maybe it's a Schechter function too. Yet you have to be careful because you have to be aware that subclumps exist. They might not all be resolved in our simulation, and also you can have a hierarchical structure cluster formation when you can merge different subclusters into a big one. So there are still many steps between linking the gas clumps to the star clusters. So the question that I want to answer now is how much of this depends on my choice of subgrid recipes, or how much of this is artificial from the simulation. So to do that, I run many more simulations when I change the parameters of the recipes. So in this one, for example, I'm changing the recipe, I'm varying something in the recipe of star formation. I multiply the star formation efficiency by a factor of 30. So fiducial is 1%, high is 30%, low is 0.1%. And I looked at different gas fraction, what it makes. To do that, I rewind in time for about 30 million years, and I run the simulation again with the new parameters. I do that only for 30 million years, because if I do it for longer, then it re-diverges, and I'm not looking at the same galaxy anymore. It doesn't have the same star formation rate, it doesn't have the same properties at all. So there is a kind of arbitrary choice in here. But what you can see is that within these changes, you can still tell apart the three gas fractions. They don't really overlap. And I can play the same game in terms of feedback. I can boost the energy of supernovae by a factor of 10. I can switch off all pre-supernovae feedback, so winds, relative pressure, photoionization, etc., everything off. And I can switch off feedback totally. And you see that again, the dispersion, the variations I see is still smaller than the differences between the three gas fractions. That tells me that the gas fractions still play the biggest role in clump clump formation and survival in terms of feedback. So having this in mind, what does it matter so much? It's because everything that we know in the local universe about giant molecular clouds, because we can resolve them, is exquisite level of details observationally, because they've been studied in great details in theory and simulations. Maybe we can export this knowledge, to these massive clumps. And therefore, if we want to do that, we have to check that if massive clumps are just scaled-up version of local molecular clouds. So all this is preliminary, but spoiler alert, no, they are not. They are larger, they are more turbulent, but they have similar densities. And you can see that in this density profile, function of radius in the clump. You see that the three cases, so the three gas fractions, they kind of reach the same value. The shaded area are just the dispersion over many, many clumps. So larger, you see they expand to larger radii in black and red, but similar central densities. So if you plug this information all together, that tells you that these clumps cannot be on the same Larson scaling relation than local molecular cloud. So therefore, it suggests different formation mechanism from massive clusters and from low mass clusters. And again, I'm opening Pandora box, so I should not say no more. If you want to hear more, these are my conditions. But again, why does it matter so much in terms of galaxy evolution at larger scale? Again, because the chemical enrichment will be different between a massive clump and a local cloud. And this has been shown already by Clark and collaborators and Kopperskopf and collaborator. They show that you have rapid, vigorous star formation in clumps, so high alpha over Fe, basically this part over there. And when you stop forming clumps, then you can go down to the low alpha over Fe when you have the transition from clump to spiral arms. So putting all these things together, we can have a look at what internal or intrinsic evolution does and what external influence does. Internally, with time, you will decrease your gas fraction. You will change the stability regime because of that. You will end the clumpy phase and move to the spiral phase. And you will slow down your star formation. From cosmological influence, what you do is to end the merger phase. You don't get any tidal excitation, so you lower your turbulence, you have less and no more starburst, and you don't boost your alpha over Fe anymore. So if you compare these two things, they're actually telling the same story. They do less turbulent, kinematically colder, thinner disk, and lower alpha over Fe. When this transition happens, internally it's at gas fraction about 20%, as I've told you, and cosmologically speaking, it's after the last merger. What is cool is that in the Milky Way, we think these are more or less at the same epoch, redshift around 1. So time to conclude. What I've told you today is that starburst is not the same as an offset above the main sequence. The response to mergers depends on whether the disk is in place. And again, Alvaro will tell you much more about that this afternoon. The disk formation and the last major merger mark two important transitions along galaxy evolution. I would say the third one is quenching. The gas fraction rules intrinsic evolution. And the transition to clump to spirals happened at gas fraction about 20%. And this is due to a change in the stability regime of your disk. And massive clumps are not just big version of giant molecular clouds in the local universe. If you want to know more about that, you know my conditions, and maybe I will stop the story here for today. Thank you.
Thanks, Florent, for this beautiful talk. I have just a quick question. Is at the beginning, when you showed the comparison of the specific star formation rate versus star formation efficiency, the galaxy, you are looking at the galaxies in redshift 10, spent most of its lifetime with the star formation, with the depletion time, which was around 100 million years or so. Yeah, this one. Yeah. So, like below redshift 1, above redshift 1, most of the lifespan of the galaxy is at, let's say, 200 million years or 150, whatever. But if you look at, you were quoting Tacony for the comparison to the y-axis, but if you look at Tacony, for example, for the x-axis, you will see that over the most of the lifetime of a galaxy on the main sequence, it's closer to 600 million years. So how do you understand that?
I think it's all a matter of time scale. How long the galaxy stays in a short depletion time after a starburst, and how many starburst events you have. So in the end, I'm showing you here only one example when we have one merger tree, basically, one star formation history. If you were to stack a series of galaxies with different mergers, different number of mergers, different frequency in between, or time scale between mergers, you will get probably a different story.
Nice talk. Can you say anything about the lifetimes of your clumps as you vary the gas fractions and your physical parameters?
The lifetime too, sorry?
Yes.
Say again?
Can you say anything about the lifetimes of your clumps as you vary the gas fractions and as you vary your physical parameters?
So I tried to look to this, and I failed. Because the problem is that you have a lot of mergers and splitting of the clumps, and in the end it would have been a very artificial results, very based on the method I will use, so I prefer not to look at that. What I can, maybe very roughly, and I guess that's what is behind your question, the massive clumps are long-lived. They survive star formation and feedback for more than just, say, 10 million years. If I want to put a number of that, I'm running into problems. And the small clouds are not long-lived, they are destroyed.
Thanks for a nice talk. You point out this gas fraction of 20% as being a crucial parameter. It sounds to me like, if you link it to a turmeric criterion or something similar, surface density of the gas is really what matters, not gas fraction. Now, gas fractions, you play with a factor of 2 changes from 20 to 40%, and you get a huge change. Yet, if you think in terms of angular momentum at a given halo mass, right, there's an order of magnitude to play with. So, shouldn't we really forget the gas fraction? What really matters is the critical surface density.
That's a tough question. Yeah, I mean, ultimately everything is linked, because the way you get to this gas fraction will depend on how much angular momentum you accrete, how much how you distribute your densities in 3D and in 2D. So I would say all this is linked. I'm talking about gas fraction because it's much easier to change in the simulation parameter, so that the parameter I can control. Then if you look in terms of distribution of densities, you do not see huge difference between these cases in the sense that you distribute the same gas differently, in the sense that you will not reach super high densities. That's what I showed in this plot of the of the density profile of clumps. Increasing the gas fraction doesn't change the central density of clumps. So the clumps are just bigger, more extended, but they are not denser. So it's all a matter of how you distribute the density in between the clumps and how big or especially extended the clump would be. So in the end, what is the real fundamental driver of instability is, I guess it's a mix of everything.
Thank you very much for a fascinating talk. I was curious whether bars play any role in terms of either observability and the progress of of your evolution? And secondly, you didn't say much about the spiral patterns, but perhaps there are some signatures there that might be of interest to us observers.
That's also a very difficult question. Yes, bars do play an important role. I would treat them more or less as spiral structure, because in the end, bars is just two spiral arms together, if you see what I mean. It's notoriously difficult to get bars in cosmological simulation. I think nobody really understands why. I don't understand why. So we don't have bars in the cosmological simulation, and I don't run the isolated simulation long enough to see bars. So I haven't looked at this in details. From the morphology of the simulation I get, it doesn't seem that I will get a bar in a high gas fraction, because the morphology is really local clump dominated. Like here you can imagine that the bar will form in maybe one rotation or a few. But here, okay, you have something elongated. It's not clear. It will change definitely the stability regime. It will change the way angular momentum is transported, distributed, and maybe it will trigger star formation at the tip of the bar. So all this will have an effect, of course.
Okay, let's thank Florent again.
Thank you.
And it's now time for our morning coffee break, so we'll reconvene at 11:20.